In this video, I wanted to cover some of the practical aspects of the Laplace transform and review some of the things that are immediately needed for the course. All right, so we're going to look at some properties, and we're going to also look at some common signals that we take the Laplace transform of. All right, so we're not going to cover everything in the way of a review of Laplace, but we're going to pick out some important things that I want you to focus on for the moment. Okay, so first of all, here's my concept of why the Laplace transform is very useful. Okay, we have over here on one hand the time domain. Okay, so we write differential equations in the time domain. We have signals that exist in the time domain. And I would call that f of t, t for time. And then over here is the S domain. We had some videos that talked about this. The S domain, sometimes people call it the frequency domain because S equals j omega. J omega is the frequency component of that, so sometimes it's called the frequency domain. And over in the frequency domain, a signal can be transformed to land over here as f of s. All right, so t for time, s for the S domain. Okay, the signals or the parameters don't mix. In other words, if you have a signal in the time domain, it's a function of time, has the variable t, and when you take its Laplace transform, the t should vanish after you do the integration, and you have just the parameter s. And conversely, over here in the time domain, you shouldn't see the s parameter showing up. So it's one or the other. Okay, the other issue is that once you have a signal over in the S domain, maybe you want to run this through some type of filter and you get a different signal, g of s. From there, you can take the inverse Laplace transform and get back to g of t. All right, so this is inverse and this is the Laplace transform. And that's how I think of it. I'm moving back and forth between domains to help me solve practical control problems. Okay, so the next thing I want to do is show you a table of transforms that comes from your textbook. I'll blow this up a little bit. And I just wanted to pick out a few that are important, okay? And we'll focus on those. All right, so first of all, this idea of superposition is important. The Fourier transform of a linear combination of signals is found by just taking the Laplace transform of each of the pieces. If I said Fourier, I meant Laplace, okay? So you take the Laplace of f1, that shows up here. You take the Laplace of f2, that shows up here. And you just do the linear combination of Laplace transforms. We're going to get to time delays a little bit later, but we'll hold off for now. Time scaling is not going to be super important for us. Shifting in frequency is not super important for us, but this differentiation property is going to be important, and so is the integration property, so is the convolution property, and a little bit later on we'll get to initial and final value. Okay, so those are the main properties that we're going to use. I did want to take the time to talk about the differentiation property right now. Okay. So if I had a signal x of t that has a Laplace transform x of s, if I take the derivative, okay, if I take the Laplace transform of that, I get this extra s showing up. S times x of s minus the initial condition. Okay, and there's a, I could take a second derivative and throw in the initial conditions as well. So many times in our class, we're going to end up assuming that the system is initially at rest. So the initial conditions will be identically zero for both x of 0 and its derivatives. Okay, so if that's the case, if we have zero initial conditions, if I took the second derivative of a signal and found its Laplace transform. Notice I'm drawing arrows here because these aren't equal signs. This is the Laplace transform takes me into this domain. Okay, So I take the Laplace transform and I would get s squared x of s, and the initial conditions are 0. So that's all that I would have. Okay, so this is a concept that we're going to use a lot. Is when you see a derivative, you just put a power of s in front of the transform of the signal. Okay, so those are some properties. Let's see what else I wanted to tell you about that. Differentiation. Integration is an interesting property. So let me show you real quickly an example with integration. Okay, let's say I had a unit step function. A unit step function starts at 0, turns on at t equals 0, and then moves up to a step of 1 for all time. Okay, what if, I call this signal u of t. What if I looked at y of t is equal to the integral from minus infinity to t, u of tau d tau. This would be the integral of that signal, okay? And the way that would work is I'm essentially looking at the area under the curve for different time values, okay? So if I started at t0, I would get the area underneath the curve between 0 and t0, okay? And if I, kept marching along in time, where this is now time t, I would just keep adding area. Okay, and so if I looked at the area under the curve, this has a height of 1 and a width of t, the answer would be simply equal to t. All right, so that's the integral of the unit step. All right, so the property says that if you take the integral of a signal, integral of f of tau d tau from 0 to t, okay, I'm sorry, that should be y of t. That would be, when you do this Laplace transform, it would be f of s, because I start with the signal f of t, divided by s. Okay? So it goes along with our intuition about the relationship between integration and differentiation, right? Integration does an undo on differentiation. And so if I multiply by s to do a derivative, I would divide by s to do an integral. Okay, so hopefully that makes some sense. The last property I wanted to quickly go over is this idea of convolution. What we had videos of in Module 2 was that convolution turned out to be the output for a linear time invariant system. Okay, so if I put in into a system, I'll call this an LTI system. Okay, if I put in an impulse and get out h of t, then I can take the same system and put any signal in, x of t, and look at the output, y of t, and what we know is that in the Laplace domain, y of s is h of s times x of s. Okay, so h of s is called the transfer function of the linear time invariant system, and I've got a whole video that I'm going to give about that particular topic. All right, so there's a quick review of the properties that we're going to need. And so what I'm wanting you to do is to just try to wrap your brain around on these properties so far, and I'm going to give you some homework to help you through that. Okay, next, I wanted to talk about various signals that you might encounter in this class and when you look at control theory. All right, so the first signal is the impulse. Remember, we care a lot about impulse response for a linear time invariant system. And so the input in that case would be this impulse function, okay? And if you have a given impulse function, you put that in as a time domain signal. When you take the Laplace transform, you just get a constant back, All right, so I'd like you to remember that. Okay, this next one, it's weird notation. He calls that 1 of t. I think he means u of t for unit step. And we talked about that just a second ago, that a unit step function is 0, and then it turns on at time 0 to be a 1. Looks like this, okay? When you plug into the integral to do the Laplace transform, this turns out to give you this transform pair 1 over s, okay? And then we just talked about this integration idea. So if I integrate a unit step, I get t. All right, so the Laplace transform is you take the Laplace transform of unit step and you divide by s and you get 1 over s squared. Okay, so those three are transforms that I'd like you to know about. Okay, the next couple that I want to talk about involve exponentials. So let's look at e to the minus at and t e to the minus at. All right, so I need a little space to talk about this. All right, so the first one, e to the minus at, I normally go ahead and write down that there's a unit step. All right, in a way that's redundant because the Laplace transform that we're looking at is one-sided, meaning when you look at that integral, it goes from 0 just to the left of 0 to infinity of the function. Okay, that's the definition of the Laplace transform. Okay, so the unit step wouldn't be necessary because we're only looking at positive time values. All right, but I go ahead and put that in just because it helps me keep mental track of I'm turning on an exponential at time equals 0. Okay, so when you look up this transform or compute this transform, it's 1 over s plus a. All right, and so here is an idea that, we talked a little bit about poles and zeros in the previous video. A pole is when the denominator divides by 0. So at s equal minus a, you get a pole. All right, and it's called a pole because if you looked at the s domain and laid it flat on its side, and you looked at the value minus a, all right. If you plotted this as a three-dimensional plot, it would blow up right above A and make a pole kind of shape. All right. So if you can't envision that, I'll try to show you that in MATLAB sometime. All right, but that's called a pole. All right, and what we do, or what we're after here, is to start looking at what I call patterns. All right, so I draw a little icon to represent a pattern, a pair of glasses that you're supposed to put on and recognize the pattern, okay? So the pattern is we have exponentials, and if you have a pole at a real pole at minus a, think of an exponential, all right? And we know what that looks like when we graph it. This would look like something that starts at 1 and decays down according to e to the minus at, all right? Okay, so that's an important one. All right, next one I wanted to talk about what happens when you have t e to the minus at. That Laplace transform turns out to be 1 over s plus a squared. So it's still a pole at minus a, but it's repeated, all right? Because it's squared, it's there twice, all right? So what's interesting about that one is that you now have two functions here. You have the e to the minus at, which I know is decaying, but then you have t multiplied by that, and of course t is growing, and e to the minus at, if I went to the green color, is decaying, and we're taking a product of these two things. Okay, so I think what you know is from your calculus classes that the decaying exponential wins, but this function sort of blips up and then decays down. All right, so this is a repeated pole, is what we call it. And this sometimes comes up in some of the work that we do. Okay, back to the table. All right, so the next transform I wanted to show you is going down this list, sine of AT. All right, that has this Laplace transform. All right, and if you think about it, where are the poles here? There are two poles, okay, because if I scroll down here, I had on the denominator s squared plus a squared. Let me just go ahead and copy the whole thing. A is on the top. This is the Laplace transform of sine AT u of t. Okay. Remember, the poles are where the denominator is equal to 0, the roots of the denominator. Okay. So if I solve for s squared plus a squared equals 0, I'll go ahead and do that. S squared plus a squared equals 0. S would equal to plus and minus j a. All right, so if I graph that, here's the real axis, here's the imaginary axis. I would have a pole showing up at plus ja and minus ja. Okay, so that's an important concept. We know what a sine wave looks like. All right, a sine wave looks like this, and it oscillates at, in this case, at frequency A. All right, and we recognize the pattern. The pattern that we're going to recognize is that when you have poles right on the j omega axis, that gives you oscillations in the time domain. Okay. All right, so similarly for cosine, all right, cosine, the transform is s over s squared plus a squared. All right. Okay, so in that case, if I looked at the poles, I still get poles at plus and minus JA. All right, and cosine looks similar to sine. There's just a phase shift. All right, so that would look like this. Remember, it's times unit step. All right, so this thing turns on at 0. Okay, but the point is it oscillates at frequency A. All right, so again, if I did a pole 0 diagram, which we'll be doing lots of these, here's a pole here and here, plus JA and minus JA. All right, so the key here is to envision this oscillation because of that pole pair on the j omega axis. Okay, next up, let's look at this particular pair. This is the last one we're going to do in this video. All right, so in this particular pair, we have e to the minus at times cosine bt. All right, and that Laplace transform is s plus a over s plus a squared plus b squared. Okay, so let's write that down. S plus a over s plus a squared plus b squared. All right, and the transform was e to the minus at cosine bt. And again, there's a unit step out in front, but I don't need to write it. We're talking about time greater than 0. Okay, so can you envision what this looks like? This would be an exponential multiplied by a cosine. Okay, so when you do that, that would look like you have this envelope for the exponential, and you would oscillate back and forth in this envelope. So it's an oscillating signal that's also decaying. All right. So what does the pole pattern look like for this particular signal. Okay, so I would take s plus a plus b squared equal to 0. I want to know where the denominator is equal to 0 to find the poles. Okay, so that'd be s plus a is equal to plus and minus jb. And solve for s. S is minus a plus and minus jb. Okay? All right, so when I graph that in the S domain, all right, here's the real part, here's the imaginary part. I would go over to the left by minus a and up by plus and minus jb. All right, so this distance over would be, this is a, and this distance up to the top here would be b, so minus a plus jb minus a minus jb. All right, so when I see a pole pattern that shows up in this configuration, I start immediately thinking of, okay, it's a decaying exponential that wiggles like a cosine. Okay, so those are some signals I want you to think about. We're going to play around with some of these in MATLAB for a homework assignment.